Okay, hello to everyone. Welcome to this plenary session. We are grateful to have George Marios Angeletos from MIT today with us. He's going to talk about beliefs and monetary policy. I don't think he needs further introduction. I mean, we are all aware of the great amount of work that he has done in several different areas. You have 40 minutes. Please, any questions you might have, please submit it to the chat by sending a direct message to me. We will leave 5 minutes at the end of the talk to pass the questions to the speaker. The floor is yours. Thank you very much.
Thank you very much. Thank you all for being here. And today I'll try to talk about sort of two bigger projects, but basically two papers. The common thing is going to be about the role of expectations and beliefs in monetary policy. And I will concentrate first on how this matters for equilibrium determinacy and how it relates to the Taylor principle and the physical theory of price level. So this is going to be more like basic questions about whether there's a unique equilibrium or not in the standard New Keynesian model. And then I'll focus on the normal or conventional equilibrium that we use to study monetary policy. And I will expand there on how information frictions and expectations matter for the empirical properties and the policy predictions of that particular equilibrium. Okay. So let me first start with the following question, the determinacy problem and the New Keynesian problem. And let me step back and let me ask you to think about some very basic policy questions, such as what determines the price level in inflation? Is it monetary policy? Can monetary policy regulate aggregate demand? Does the ZLB, the zero lower bound, during the liquidity trap, trigger the deflationary spiral? And our first inclination, at least as applied macroeconomics, would be to give very simple answers to this question. You know, monetary policy determines the price level. Yes, monetary policy can regulate aggregate demand by controlling its policy and instrument the interest rate. And yes, the ZLB triggers a deflationary spiral. And that's how we understand perhaps the Great Recession. But the inconvenient truth is that these answers that I just spelled out are correct only under a particular selection of a particular equilibrium within the New Keynesian model. And the truth is that the New Keynesian model is written with multiple equilibria that all have to do with forward expectations. And there is a perennial issue on how we select equilibrium within the New Keynesian model and a larger class of monetary models. And different selections lead to different policy predictions, different structural interpretations of the data. Okay? And I need to remind you that this goes back to something that was, first highlighted by Sargent and Wallace back in '75, which is that the same path for the nominal interest rate is consistent with multiple equilibrium paths for inflation and output. That's the key problem. It goes back to Sargent and Wallace. It has been stated in many different ways, in many different models, and has been inherited by the main paradigm we use nowadays to understand monetary policy. So in response to this multiplicity of equilibria, what do we typically do? The conventional practice is to assume that monetary policy does not simply set interest rates, but rather commits on a specific feedback rule, known as a Taylor rule, where the central bank commits to raise interest rates more than one-to-one in response to inflationary pressures. That's known as the Taylor principle, or as very hawkish monetary policy, as very aggressive monetary policy response to inflation pressures. And this suffices to select a unique equilibrium. This equilibrium that is selected this way is known as the fundamental or the minimum state variable solution of the New Keynesian model. That's the one we use when we teach the New Keynesian model. That's the one we use when we take richer DSG versions of these models to the data. That's the one we use to guide monetary policy. Okay. But there's an alternative approach, which is known as the fiscal theory of price level. I will explain later on what exactly this is, but let me summarize it here as it's an alternative approach that uses the government budget, the temporal government budget, to pin down a different equilibrium than the usual one. And in this equilibrium, debt and deficits emerge as key determinants of inflation and real economic activity. So there are two different approaches. There's a conventional one, which I would say is the dominant. There's the fiscal theory of price level, which is maybe it's more erratic, more exotic perhaps, less conventional, but within the model, they're equally logically coherent. Hence, there is a conundrum. Which one is the right one? Okay? And there has been a debate for 40 years now about which solution is the right one. And the debate is not easy to resolve on logical grounds. It's either easy to resolve on empirical grounds, because both of these selections boil down at the end of the day to commitments about what fiscal or monetary policy will do off equilibrium. And such commitments, or if you want, off equilibrium threats, are not easy to test because off equilibrium paths are never realized. So explain this more, but let me tell you what we're going to do. What we're going to do is going to revisit this problem and from a new perspective. And the new perspective will be to try to translate the determinancy problem from a mathematical eigenvalue problem to something that you can understand more as a coordination game, in particular as a dynamic coordination game. So we'll equate the multiplicity of equilibrium to a particular infinite chain. What is the infinite chain here? We're in a forward-looking model where current agents may decide today, may find it optimal today to respond to sunspot or payoff irrelevant histories if they expect future agents to respond in a similar way, and sort of you wish to reward them for responding to sunspots. But future agents will themselves do that only if they expect agents further in the future to do that in perpetuity. So the multiplicity that is in the New Keynesian model, the larger class of forward-looking models, hinges crucially on this infinite chain that we expect future agents to keep coordinating on a particular payoff irrelevant equilibrium in perpetuity. And what we're going to show is that if you introduce seemingly small perturbations in social memory and intertemporal coordination, or small departures from common knowledge in a particular way, that will break the infinite chains, will make the multiplicity of equilibrium to disappear, and will give you always a unique equilibrium. This unique equilibrium, this unique rational expectation equilibrium will be the standard, fundamental, or minimum state variable solution of the model. This is the same as the one selected by the Taylor principle, but it will no more rely on the Taylor principle. By the same token, you could tell policymakers, even if you violate the Taylor principle, the equilibrium may be unique, number one. Number two, there will be no room for the fiscal theory of price level to select a different equilibrium because there's no other. So this will lead to a different way to think about both the Taylor principle and the fiscal theory of price level. Okay, enough with my lengthy introduction. So let's put some math in my words. So I will start with my simplified three-equation New Keynesian model. It's not exactly the standard one, but it's very close to the standard one. And I will skip a little bit the micro foundations behind it, but let me give you the basic ideas. Three equations, the dynamic IS equation, the Phillips curve, and the Taylor rule. Let's focus on the dynamic IS equation. This has two parts. Y equals C is just market clearing because there's no capital. We're in the version without capital. The second part is an aggregate consumption function. I want you to think the economy is populated by overlapping generations of two period-lived consumers. If you think of two period-lived consumers, their individual consumption will depend on their expectations of what? Of current income and next period income. And will also depend on what are real returns, real interest rates between today and tomorrow. So if you think of individual consumption, these are the key determinants. The individual expectations of this income and interest rate will determine individual consumption. And if you aggregate across all consumers, you are going to get that aggregate consumption depends on the average expectations of permanent income and real interest rates. And this is just a discount rate shock or a demand shock. Okay? So note that here I was careful to describe consumption in terms of the entire optimal consumption function, as opposed to merely the Euler condition, which is merely an optimality condition that forgets budget constraints. Okay, so I'm careful here to have the whole optimal consumption function. But I also want to reassure you the following, that if I make the assumption that all consumers have the same information, so that I replace this average expectation operator with the standard rational expectation operator, and I use the fact that YT is equal to CT, then this equation reduces back to the standard Euler condition for an infinite representative agent consumer. So really what I'm doing here is I'm unpacking the macro foundations of what is behind the standard dynamic IES or the standard Euler condition, and thinking of it as a consumption function. Second part, Phillips curve, for simplicity, is going to be a static Phillips curve. Later on, I will have the full one. Third equation, just the Taylor rule that tells you the interest rate as a function of an intercept that may be stochastic, may depend on the state of the economy, and some response to inflation. Okay, that's the model. Now let me do the following super complicated thing. That's a joke. I'm going to simply do the following. I know y equals c. So let me replace on the right-hand side of this equation y and yt plus 1 with just ct and ct plus 1. So this will give me ct as a function of average expectation of ct and ct plus 1. Let me also note the following. Well, inflation is just kappa times ct. So inflation can also replace it as a function of consumption. The interest rate is a function of inflation, which is a function of consumption. So basically, all the objects on the right-hand side of this equation, I can replace them as functions of current and future consumption. So I can reduce these three equations into a single equation on a single variable, where the single variable is consumption. And this equation looks like this. What I've written here, I've written consumption today as a function of average expectation of consumption today and consumption tomorrow, and some shifter theta t. Theta t is just a transformation of the underlying demand, supply, and monetary shocks. So think of theta t as the fundamental. And this equation now you can think of it as a game among the consumers, where this is the average best response about the consumers. And I'm telling you, the economy reduced to a game where the average consumption today depends on average expectations of consumption today and tomorrow. What is this game? It looks like a beauty contest. What does the strategic complementarity in this game captures? Well, they summarize all the GE feedbacks in the economy. What are the GE feedbacks? There are three of them. One is the Keynesian cross, or the feedback between income and spending. If the other consumers spend more, I have more income, I want to spend more. That's a source of complementarity. There's another feedback, which is if other consumers spend more, output will be high, demand will be high, inflation is going to be high, which for given nominal interest rates translates to lower real interest rates, which will make me spend more. So the feedback through the Phillips curve is another source of strategic complementarity. And finally, if other consumers spend more and there's a boom and the economy is overheating, then monetary policy may react by raising interest rates, and that would discourage spending. So the response of monetary policy is a source of strategic stability. But all these feedbacks, you can think of them as just special case of what goes on behind this game. Yeah? So why I like this representation of the economy? Because now you can think of the economy, as I said, as a game, and you can think of the issue of multiplicity as a question about how strong the complementarity is in this game instead of something about eigenvalues in the dynamic system. Okay. Now, what I want to do is to complete the model, I need to specify the information and the underlying shocks. So here I'm going to have two types of exogenous shocks. The shocks to fundamentals, and payoff irrelevant shocks, sunspots. So for simplicity, let me assume that both of them are IID over time. In the paper, we'll have general stochastics, but for simplicity here, I want you to think that both the fundamental and the sunspot are IID. And also for simplicity, maybe they are normally distributed. Now, what is the state of nature? The state of nature is just the entire infinite history of the realization of these variables between the infinite past and today. What is going to be my equilibrium concept? It's going to be just standard rational expectations equilibrium, although potentially based on limited information about the current and the past. And because I'm in a linear model, I'm going to be focusing on linear equilibrium, which means that I will be looking at possible solutions to that game that are where C is a linear function of the infinite history of sunspots and fundamentals. That's it. That's my equilibrium concept. So standard rational expectations equilibrium, which I can define it for arbitrary information structures. I haven't told you yet what the information structures are. So now let me go to first tell you what happens with full information, which is the standard model, and then how I will go away from it. Now, I had before a game where consumption today depends on consumption today and tomorrow. But if we have full information, if all consumers share the same information, then of course there's no uncertainty about contemporaneous consumption. So you can take contemporaneous consumption outside the expectation operator, solve out for current consumption, and you can reduce it to a simple forward-looking equation like this, which tells you consumption today depends on the fundamentals and expectations of consumption tomorrow. That looks like the standard Euler equation, except that this delta encompasses all the other GE feedbacks. What is the standard approach? Is you look at solutions to this forward-looking equation. Because this is a forward-looking equation, it's immediate to see that there is always a forward-looking solution. In particular, remember that for simplicity here, I have assumed that theta t is IID. So if you assume for a solution where consumption depends only on the fundamentals, then your expectations of consumption tomorrow are pegged at 0 because future fundamentals are unpredictable. So immediately you see that the unique fundamental or minimum state variable, as it's otherwise called, solution is simply that consumption is driven by the fundamental, which simplicity here is C equals theta t. So that's always a solution, okay? That's a standard solution. And it simply tells you that spending and inflation today depend on interest rates today or expectations of interest rates tomorrow. So let me remind you, in particular, that behind this theta t is the intercept of the Taylor rule. So this solution simply tells you that if the mandate authority today increases interest rates, theta t is going down, consumption and inflation will go down. That's the standard prediction. But now let's ask the following question. Is this the only solution? And the standard answer is it depends on phi, which was the slope of the Taylor rule or the responsiveness of monetary policy, or equivalent on delta. In particular, here I'm not showing you exactly the details, so you can see the formula for delta here. But basically, when the Taylor principle is satisfied, this forward-looking coefficient is smaller than 1. And otherwise, it's higher than 1. So this is like saying that the eigenvalue of the dynamic system shifts from inside versus outside the unit cycle, depending on whether phi is higher than or equal than 1, depending on the Taylor principle satisfied. So the standard approach is impose the Taylor principle by assumption, then you have a unique solution and you move on. What we're going to tell you is that even if you don't impose the Taylor principle, this is going to be the unique solution. Before I tell you how we get it, let me tell you what is the plethora of equilibria you get if you have full information and if the Taylor principle is not satisfied. So as I said, if the Taylor principle is satisfied, this is the standard equilibrium is the unique equilibrium. If it's not satisfied, you can construct a sort of double continuum of equilibria that can all be written as linear combinations of 3 objects. The fundamental solution and two other components. So first of all, let me explain what are those two components. This component, I'm written it here, it's just a function of the infinite history of sunspots. So this is a pure sunspot component that has nothing to do with either past, current, or future fundamentals and drives up and down consumption. This is what? This is a component that depends on the history of past fundamentals. Now, this can be a little bit confusing because I'm giving you something that looks as a function of fundamentals, but note the following. You are in an economy that is purely forward-looking, and the current fundamental is a sufficient statistic about where the economy is going in the future. So past fundamentals are payoff irrelevant. Past fundamentals are effectively sunspots. So this is another sort of sunspot solution where the past fundamentals are playing effectively the role of a sunspot. And you can see this correlation from the very fact that the mathematical structure of this and this is exactly the same. Okay, so this is a pure sunspot, and this is a sunspot-like pseudo-fundamental solution. And what does this equation tells you? It tells you, well, you can take arbitrary linear combinations between the fundamental solution, this backward-looking pseudo-fundamental solution, and the pure sunspot. And any of these combinations is an equilibrium. Now, in particular, there's an equilibrium where this B is 1, and that tells you that along this equilibrium, consumption and inflation today do not respond to current monetary policy. And instead, they respond to the history of monetary policy. But now note the following, the history shows up with a negative. So there are equilibrium now with the following property. If monetary policy contracts today, raises interest rates, nothing happens to consumption inflation today, and tomorrow there's a boom. So contraction in monetary policy becomes expansionary by selecting a different equilibrium. That's just to illustrate how you can turn completely upside down the standard predictions we have from the new Keynesian model. Now, what's going on? Why you have all this multiple equilibria? Because of the infinite chain I anticipated before. For example, how could it be that the agents are responding to a pure sunspot? Well, because if they expect future consumers to respond to the sunspot, particularly if they respond if you expect that a positive sunspot today will cause a boom tomorrow, then you want to spend more today because you're expecting more income in the future. So this way you can create a self-fulfilling boom out of a pure sunspot. But also how it could be that the monetary authority raises interest rates and you don't reduce your spend today, because if in response to contraction in monetary policy, you respond for some reason consumers in the future to create a boom, then that expected boom can undo the contraction effect of monetary policy today. So this way you can create a self-fulfilling boom out of an increase in interest rate. So the key thing in all that is the expectation that other agents will respond in the future in a particular model way, and this expectation is itself sustained only because you expect other agents in the further future to keep doing that in perpetuity. And what we'll do now is to show you how fragile this kind of infinite chain is going to be. So now I'm going to go away from full information, in particular from common knowledge, in the following way. I want you to envision the economy as follows. Here I have the formal adaptation, and here I have like how you can envision this adaptation. I want to think that in every period, a young consumer who is just born learns perfectly the current fundamental and the current sunspot. But he may not know perfectly the history of the economy. He may not know past fundamentals and past sunspots. Remember, past fundamentals and past sunspots are payoff irrelevant. They are payoff irrelevant, but they are crucial for supporting these other equilibrium. So here I'm going to introduce an information friction, not only about what happens today, but rather about what is happening, may have happened in the past. So in particular, I will assume that with probability lambda, a young consumer learns nothing more than the current shock. And with probability 1 minus lambda, she inherits the information of a previous consumer. That previous consumer may have known more stuff about the past or maybe not. So lambda parameterizes the extent to which you inherit or lose memory or information as we go over time. So that. In particular, if lambda is 0, then there's no memory loss. Everybody will know the infinite history. For lambda small enough, everybody, almost everybody, will know arbitrarily long history. In particular, the distribution information sets, so if you pick an arbitrary agent I in period T, his information set is given by a finite history of current and past shocks up to some S, some past date S, and this S follows a geometric distribution in the population. And as lambda gets closer to 0, you get bigger and bigger masses of agents who know longer and longer histories in the economy. Okay? I'm going to say it like this. In the limit as lambda goes to 0 from above, as the information friction becomes vanishing, almost all agents in the economy have arbitrarily long memory, actually both about the exogenous shocks and the endogenous objects. But at the same time, memory is not infinite in the following sense. For any lambda positive, even arbitrarily small, the agents who know, the mass of agents who know histories of very, very, very long length is vanishing. Okay? So there are no agents with infinite, truly infinite memory, even though there are many, many agents with arbitrarily long memory. What is going to be our result? Our result is that even though with lambda exactly equals 0, you have multiple equilibria, as long lambda is positive, even epsilon, you get immediately a unique equilibrium, and that unique equilibrium is the MSV solution. And that's true is regardless of delta or equivalently of the slope of the Taylor group. And also no matter of how small or big lambda is, no matter how severe that friction is. Okay? So that's our kind of discontinuity, and many of you may recognize here, at least in spirit, a similar discontinuity as in the literature on global games or the literature that goes back to Rubinstein. That you start from common knowledge, you make a seemingly tiny perturbation, and suddenly all the multiplicity disappears. So I'm not going to go through the math. I will only give you a little bit of a sketch of the proof of the logic. Okay. So remember that the key thing here for sustaining multiple equilibria is that you need to be confident that future agents will keep responding to a sunspot. Or you need to be confident that future agents will keep coordinating. But now if you expect that future agents will forget in the future, them forgetting in the future what were the shocks or what we were doing today is effectively the same as saying that the perceived complementarity fades with horizon. As I'm looking further and further in the future, I expect the agents not to be able to coordinate with me. Why? Because I expect them to forget the history. I expect social memory to have disappeared. So introducing this fade in social memory is akin to making the perceived strategic complementarity get smaller and smaller as you look further into the horizon. But if there is some sufficiently long date in the future such that the complementarity is small enough, then from that point on, you expect the agents to play the fundamental solution. But if you expect the agents from some future point to play the fundamental solution, then by backward induction, you can deduce that we cannot respond to the sunspot today, so the unique solution today as well has to be to play the fundamental solution that gives you determinants. That's the sketch of the proof. The math is just I'll skip them, but that's what they do. And a more narrative way to say the proof is the following. Look, I'm a current agent. I'm deciding whether to respond to a sunspot or to a payoff relevant history. If I knew, I see the sunspot clearly. If I was 100% confident that all future generations will keep seeing the same sunspot clearly, then I can be confident that they will coordinate with me and I can respond to the sunspot. But if I worry that agents far in the future will fail responding to the sunspot, either because themselves they will not see it, or because they worry that agents further in the future will stop seeing it, will forget it, then I will find it optimal not to respond to the sunspot, and hence you get determinants. That's the basic idea. Okay. Again, you see that the key thing that I did here is to break common knowledge between current agents and agents far, far in the future. So this is similar to breaking common knowledge in static coordination games or global games, standard global games. Okay. The difference here is that the coordination game is over time. Conceptually, at the end of the day, it's all about breaking common knowledge. So as in the global games literature, I want to give a warning that not all perturbations of common knowledge will break multiplicity. There's a literature about how prices, public signals, and so on maybe can bring back multiplicity. But I also want to highlight that because this is dynamic coordination, and it's really about coordination between today and the infinite future, the kind of common knowledge that is required for this kind of coordination may be much harder to sustain in practice. It's not just about me and you observing a public signal today. It's me and you, me and my grandkids being able to share the same information. And that's a much harder type of coordination. I will skip the robustness here for the sake of time. There are different ways to think about the multiplicity. We'll try to think more of multiple equilibrium in a recursive form. This introduces some complications about, such as, could it be that instead of trying to keep track of the infinite history of exogenous shocks, maybe we efficiently summarize infinite history, some sufficient statistics, such as past inflation, past consumption, and we use these objects as coordination devices. And we have results that tell you that even with endogenous coordination devices, even with perfect knowledge of past outcomes, you can find perturbations that kill the multiplicity. Okay, bottom line, you can get rid of the multiplicity and select the unique solution. I did this as a simple version of the new Keynesian model, but the result extends more generally. So for example, suppose that I have a more complicated, perhaps even a Hank-style version of the new Keynesian model, where consumption today depends in flexible way on expectations of income and interest rates in the entire future. I have a standard Phillips curve, forward-looking. I have more complicated monetary policy rule. I could even add forward-looking terms in the policy rule. Well, the math of the proof gets a little bit more complicated, but the logic goes through. So again, you can have uniqueness. Yeah. So bottom line so far, let me check my time. So I have 10 minutes. Am I right?
You have 10 minutes, including the questions. So
okay,
like
okay.
About 6 minutes.
Perfect. Perfect. Okay. So bottom line, you can get rid of the determinants equation. What does this mean? What are the applied lessons? Okay. So I got rid of the equilibrium determinacy, but that doesn't mean that you should not necessarily worry for something like sunspot fluctuation or animal space. Even when there's a unique equilibrium, even if you start with more simple models, there's no coordination problem, there's a unique equilibrium, you could still have a room for sunspot-like fluctuations, by which I mean the following. Fluctuations that occur along the unique equilibrium but are not tightly connected to fundamentals. That could be because of overreaction to noisy public news in environments with complementarities. That could be because of independent shocks to higher order beliefs, or related forms of boundary rationality. So even if you have unique equilibrium, but you relax full information, you have room for such a fluctuation. In that case, a monetary policy that responds more aggressively to inflationary pressures will indeed help stabilize the economy against this kind of sustainable fluctuation. But now know that you have recast the Taylor principle from something about off-equilibrium threats that give you equilibrium selection to an on-equilibrium stabilization. So it's like making the Taylor principle something more practical, perhaps like how actual policymakers are thinking about it, rather than what is truly in the current one. What about the fiscal theory price level? Well, the fiscal theory price level, basically, starting with the new Keynesian model, answer the fourth equation. What is the fourth equation? So far we had the IS curve, the Phillips curve, the monetary policy, and we're looking at solutions. And we had forgotten, if you want, the fiscal authority. Now, if you bring the fiscal authority and you think of the intertemporal budget constraint, you get that the real debt should equal the present value of surplus. So ask the following question: how is this equation is satisfied? And does it matter for inflation and output how we satisfy this equation? So the conventional approach, the textbook approach, the DSG approach is the following. We look at the three equation model, we pin down inflation and the price level from the fundamental solution of this model. So you look at this equation, you say, okay, P is pinned down by the fundamental solution, B is historically given. Well, it better be that the fiscal authority adjusts current or future surpluses to make this equation hold. That's a conventional approach. That tells you then that debt and deficits don't matter for inflation and output. And you have Ricardian equivalence. Why you have a Ricardian equivalence? Both because there are no liquidity constraints, finite horizons, and the like, but also because you have selected the fundamental solution. This requires fiscal policy to adjust deficits to make sure that this equation holds. But there's a more erratic, but equally logical approach, which is no. The fiscal authority can pick any path it wants for the right-hand side of this equation, any path it wants for deficits. And then what should happen is that the price level must adjust so that this equation holds. Because if you assume that the government cannot default, then this equation must hold. And it better be that the price level in the economy adjusts to make sure that the real debt burden matches the present value of surplus. That's the basic fiscal theory price level. And it's fully coherent within the standard New Keynesian model, as long as what? You pick a solution for the price level different than the MSV solution and the foundation solution. So effectively what the fiscal theory price level does is to pick one of the sunspot solutions of the model. That's logically coherent, and some may have argued that it's empirically relevant. And what effectively I've told you here is that once you perturb intertemporal coordination, even minimally, that option is not anymore possible. So I could summarize it with this graph that in the standard literature, you think that, well, I could have determinacy either with the Taylor principle holding and fiscal policy being Ricardian, or I could have determinacy with the Taylor principle not holding and fiscal policy being non-Ricardian. And here what I'm telling you is that once you have our perturbation, you get determinacy for free, whether the Taylor principle holds or not, but fiscal policy has to be Ricardian. If fiscal policy was non-Ricardian, you are effectively committing to violate the temporal budget constraint of the government, and that leads to equilibrium non-existence. Okay? So I spend all my time, unfortunately, on telling you how you get rid of the equilibrium selection problem. I will finish with one word, two words, and then open the question for questions. So far, what I did is I look at the standard model. I noticed that the standard model had common knowledge of sunspots and payoff relevant histories. Remove that kind of common knowledge and tell you how you can kill all non-fundamental equilibria. But I maintain common knowledge of fundamentals, and in that sense, I maintain perfect coordination along the fundamental equilibrium. So now let me tell you very quickly what happens if you relax the assumption of common knowledge about fundamentals or the common knowledge about the future. Okay? And I will do that I will illustrate it with a paper, with an older paper I had. So I want to ask you the following question. Okay, now we're focusing on the fundamental solution. I'm focusing on a situation where the ZLB binds, and I want to ask the following question. Because the ZLB binds for a while, current interest rates cannot be used to stimulate the economy, but the monetary authority can promise to keep interest rates low after we exit the ZLB. So it can offer forward guidance that monetary policy will remain lax in the future. And that's the following question. How does this kind of forward guidance, how effective it is to stimulate demand today? Now, in the standard model, if you ask this question, the answer turns out to be very surprising, perhaps pathologically so. Promising lax monetary policy in the far future can have incredibly large effects on consumption and inflation today. Why? Because there are a lot of G feedbacks from expectations of future income to expectation of future inflation and income further today. And as you pile up these feedbacks, you are working effectively with the deflationary spiral in reverse, and that gives you forward guidance being extremely powerful. But forward guidance is extremely powerful because you are coordinated with future agents to respond to this kind of news. So what we did in this paper was to relax that kind of common knowledge. So I want you to think, okay, today you have news of lax monetary policy, but maybe those news are not common knowledge. There may be a little bit of friction. So what I'm going to show you in this figure is the following. Focus just on the red line. I will keep the friction constant and small. Let me not tell you how I parameterize it, but I parameterize it in a way that's consistent with evidence and expectations, but let me just call it modest. And for given friction, I will vary the horizon of forward guidance. That is, whether we are going to exit the ZLB in 2 years or 4 years. And I will ask how the given friction attenuates the power of forward guidance relative to the standard model. And what you can see here is the following, that as you go further and further into the future, as the horizon increases, this attenuation gets larger and larger. So the bottom line is that small frictions can also make the monetary, current consumption and inflation, current aggregate demand, much less responsive to forward guidance, especially when that forward guidance is further in the future. Why? Because again, you are attenuating these complementarities, this coordination, and the further into the future you look at, the more this attenuation, so the more the dampening also forward guidance. So let me stop here, and I already overshoot.
Yes, sorry
for that.
Okay, so we have time for